So now friends, we are going to talk about frustum of a cone. Now what is frustum of a cone? Now frustum of a cone is a thing which you generally encounter in the day-to-day life quite often. Now a bucket of water is generally a frustum of a cone. In fact, a tumbler is also a frustum of a cone. So how exactly do you get a frustum of a cone? Now as we are saying that it is a frustum of a cone, it has to be naturally derived from a cone. So let's take a cone. As you can see, this is a right circular cone, a solid cone. Now if I cut this cone parallel to the base of a circle, so basically this is the base of a circle. Parallel to this, if I cut it like this, so as you can see, this is parallel to the base of a circle and perpendicular to the axis of this particular cone. So if I cut this cone that way, then the original cone is cut into two separate parts. One is another smaller cone and the other part is what is called the frustum of a cone. So basically the whole agenda here is, if we have a bigger cone and if we cut this cone parallel to the base of the circle or perpendicular to the axis, then the cone is divided into two parts, a smaller cone and the frustum of a cone. Now in this particular section, we are going to explore more about this frustum of a cone. So right now, let's consider a few entities that we should need to know about this so that we can calculate important things about this frustum, meaning the slant height of the frustum, the volume of the frustum and the lateral surface area and the total surface area of the frustum. So for that, let's take the radii and the height of the larger cone in terms of 1. So basically what I mean is, this frustum that is created has two bases. One is the original base, let us call that as base 1, and the new base, which is the smaller base, the smaller circle, which is apparently the base of the smaller cone as well. Because if you notice, when I cut it, the base that is created for the upper part of the frustum, so the smaller base of the frustum is nothing but the base of the circle of the smaller cone as well. So let us call that as base 2. So this is base 1, this is base 2. Now, as I said, we need to define a few entities. So for the original cone, let's call the radius of that original cone as R1, the height as H1 and the slant height as L1. So as you can see, these are the three entities for the original cone. So this clearly suggests that base 1 has a radius of R1. This height is H1, this slant height is L1. Now for the smaller cone, since we called the base as base 2, let the radius of that particular base be R2, let that height be H2 and let that slant height be L2. So these are the entities that we have defined: R1, H1, L1 and R2, H2 and L2. So now on the basis of these 6 entities, we have to talk about the slant height of the frustum, the volume of the frustum and the surface areas of the frustum, because we are not really interested into that smaller cone, because once we get the dimensions of the smaller cone, getting the volume and the surface areas is very easy, because we already know the formulae for the volume and surface areas of a cone. But what we don't know is the formulae for the volume and surface areas of this particular new thing that we have generated, which is a frustum of a cone. So now, before getting to the real part, before getting how to find out the volume and the surface areas, let us see one important thing where we have to relate these 6 things. And how are we going to relate this? Is by using the concept of similar triangles. Now, if anyone does not know what similar triangles are, just in case, then I'll just give you a small quick glimpse of what similar triangles are. So here are two triangles. So basically, similar triangles, as the word suggests, is not exactly congruent triangles. Congruent triangles are those triangles which are absolutely equal in terms of everything. similar triangles, as the word suggests, are similar in nature. So basically ABC and DEF, these are two triangles I'm talking about. If you see, they are similar in nature but they are not congruent. So basically if two triangles are similar in nature, what generally happens is, if I say that triangle ABC is similar to triangle DEF, this is the symbol that we use for similarity. As for congruency, we used to use the another kind of a symbol where there used to be an equality sign as well. But for similarity, this is the symbol. And if two triangles are similar, you will notice that if I say ABC is similar to DEF, then angle A has to be equal to angle D, angle B has to be equal to angle E, and angle C has to be equal to angle F. And when this happens, when these two triangles are similar, then I can say that AB upon DE is equal to BC upon EF and is equal to AC upon DF. So basically what it means is the sides from one triangle to the other are not equal, but they are proportional to each other. So basically this side upon the corresponding side of the other triangle, that ratio has the same ratio as the other side maintains. So basically this upon this is equal to this upon this is equal to this upon this. That is what is happening. The corresponding sides of these two triangles maintain a ratio which is equal to all the three parts. So that is what happens in similar triangles, and this is the concept, my dear friends, which we are going to apply here. So now let's try and figure out the two similar triangles that we are going to get here. And these are the two similar triangles. The bigger one, which is a part, rather the right angle triangle, which is used for the original big cone, that right angle triangle, and the right angle triangle for the smaller cone. These two right angle triangles are similar to each other. Why? Because you can see there are two right angles, so these two angles are equal, plus that original angle at the apex, at the vertex, is common to each other. Now if two angles are corresponding angles are equal, then the third angle has to be naturally equal, because if one angle is A, second angle is B, the third angle has to be 180 minus A plus B. So that is the case in both the triangles. So both these triangles are absolutely similar to each other. Now how does that help us is, that will help us get this. R1 upon R2 is equal to H1 upon H2, and that is going to be equal to L1 upon L2. So these are the three things that we are going to generate because of this similarity. Now, after understanding this, we have to get into the frustum, right? So the frustum, let's say, has a slant height L. Let's say it has a vertical height H, and let's say it has the base radius. Naturally the base radius is R1 and the base 2 radius as R2, right? So these are the three things that we already know about the frustum. So we can clearly understand from this that the slant height of this particular frustum L is nothing but L1 minus L2. This is one thing that we can directly understand from this particular thing. One more very important thing is the volume and the surface area, which is what we are basically targeting. I am going to give you the formula for both of these directly first about the frustum. Now let's forget about the cone at the top, because we have already derived the results which we are going to utilize to prove the volume and the surface area. But first let me give you the formulae of the volume of a frustum and the surface area of a frustum, and here they go. The volume of a frustum is 1 by 3 pi times h times R1 square plus R2 square plus R1 R2, and the curved surface area of the frustum is nothing but pi into L into R1 plus R2. So these are the two formula which are required in the problems for the applications of this particular shape of which we call the frustum. But as I said, I would like you to understand the proof of this particular formula. How have we generated these two formulas? Rather, you can directly use these formulas in the problem, but I would encourage you guys to understand how we have derived this, because always, as we have heard, curiosity always wins. So if we are curious about how we get these formula, we are going to definitely learn a couple of things more which are going to benefit us, not here, if not here, then probably somewhere else, and we are going to definitely increase our knowledge base. So let's understand how we are going to derive these two particular formula, basically the volume of the frustum and the curved surface area of the frustum. So now let's move ahead and try and understand, try and figure out how are we going to use them. So we know that about the frustum we have three things. One is the slant height of the frustum, which is L, which is nothing but L1 minus L2. We also know the height of the frustum, and the height of the frustum is H, and we know that height can be now written as H1 minus H2, right? And the base radius is R1, and basically the bottom base is R1, base 1, and the base to the top base has a radius of R2. These are the things about the frustum which will be generally given to us in the problem, and that is what the formula has. If you notice, the volume of a frustum, which is nothing but 1 by 3 pi times H R1 square plus R2 square plus R1 R2. There H is the vertical height, R1 is the bottom base, and R2 is the top base. And likewise, in the formula of the curved surface area, pi times L times R1 plus R2, L is this slant height of the frustum, and R1 and R2 are the bottom and the top radii respectively. So now let's see how are we going to proceed. First thing that we got to understand is that the volume of the frustum is nothing but the volume of the original cone minus volume of the new cone. So basically what we have written here is volume of the larger cone minus volume of the smaller cone. And we know that volume of a cone is nothing but 1 by 3 pi r square h. So in that case, here volume of the frustum is going to be 1 by 3 pi r1 square h1 minus 1 by 3 pi r2 square h2. So now the interesting thing here is we don't have h1 and h2, both of them given to us for the frustum. h1 and h2 are the heights of the original cone and the new cone. These two entities are not going to be given to us for the frustum. So we have to find out h1 and h2 in terms of the given quantities, which are r1, r2, h and l. So let's see how can we do that. Now we have to use this particular result. So now using this particular result, we are going to get r1 upon r2 is equal to h1 upon h2, right? So in place of h1, we are going to write h plus h2. Right, from this particular equation, h is equal to h1 minus h2. So h1 can be written as h plus h2, which is what we are going to substitute there. We are just using the first equality, we are not using the second equality as of now. So this is going to be h upon h2 plus 1. So now this further gives us R1 minus R2. Since our target is H2, we need to make sure that we have H2 separately. So we take the 1 on the left hand side. R1 upon R2 is H upon H2 plus 1. 1 is taken on the left hand side. So we have R1 upon R2 minus 1 equal to H upon H2. So therefore, this gives a result R1 minus R2 upon R2 equals H upon H2. So therefore, we have H2 as HR2 upon R1 minus R2. So this is a result for H2 that we have figured out. Right, now we can just simply substitute this value of H2 in this and find out the value of H1, and that is what we are going to do. From this we have figured out that H1 is nothing but H plus H2. So therefore H1 is going to be H plus H2, and H2 is HR2 upon R1 minus R2. So further solving this, you are going to get HR1 minus HR2. That minus HR2 is going to get cancelled with HR2 here, and you are going to get H1 as HR1 upon R1 minus R2. So these are the two things, as I was talking about, which won't be given to us in the problem. What will be given to us is the height of the frustum, the bottom and the top radii, and the slant height of the cone. So let's see how are we going to find out the volume of the cone, volume of the frustum rather. So therefore volume of frustum, as I said, is going to be volume of the larger cone minus volume of the smaller cone. So that now is going to be 1 by 3 pi r1 square h1, right? Because 1 by 3 pi r square h is the volume of a cone. So for the larger cone, it's 1 by 3 pi r1 square h1. So it is going to be h r1 upon r1 minus r2 minus the volume of the smaller cone, and the smaller cone has the volume of 1 by 3 pi r2 square h2, and h2 is nothing but hr2 upon r1 minus r2. Now let's start simplifying this. So here we have 1 by 3 common, rather 1 by 3 h common, 1 by 3 pi h common. Now as you can see, what is left is pi by 3 and h is taken out. We have r1 cube minus r2 cube upon r1 minus r2. Now this can be written as pi h upon 3. Now in the numerator we have a cube minus b cube. So r1 cube minus r2 cube can be written as a minus b into a square plus ab plus b square upon r1 minus r2. I repeat the formula that we used here. We use the formula a cube minus b cube is a minus b into a square minus ab plus b square. Rather a minus b into a square plus ab plus b square. That formula has been used. A is r1 and b is r2. Now using that formula we got this. These two things have been cancelled, and then we get the volume of the frustum as what I had given to you at the start. It's nothing but 1 by 3 pi times h into r1 square plus r1 r2 plus r2 square. My bad, I haven't written the r2 square over here. So yes, this is how it goes. This is the formula for the volume of the frustum. Now if you notice, you can write this volume of a frustum in a more interesting way as well. Again, how? Let's see that. If we take h by 3 common, right? If we take h by 3 common, then we have pi r square, right? Pi r1 square rather, and pi r1 square is area of base 1, right? Then we have pi r2 square, which is area of base 2, and then we have pi r1 r2, which can be written as root of pi square r1 square pi square r1 r2. So basically which goes into the root. So now then we have pi r1 r2, which can be written as root of pi square r1 square r2 square, which can be further written as root of pi r1 square into pi r2 square, and hence this can be further written as area of base 1 into area of base 2. So this is how the volume of a frustum can be written. Very interesting, isn't it? Definitely might be a bit lengthy, definitely might be a bit confusing here and there, but then if you look at it as a whole, a lot of things to understand from this particular derivation. Starting from the similarity of the triangles involved, we found out this. Then understanding what are the things that won't be given to us in the frustum, because H1 and H2 are not a direct part of the frustum, they are a part of the cones that were utilized in forming the frustum. So we found those values in terms of the values which will be a part of the frustum. So basically H, the height of the frustum, R1 and R2, the radii of the bottom base and the top base, and then using all these values, we found out, we derived the frustum volume as the volume of the bigger cone minus the volume of the smaller cone, and then simplified it to this pi h by 3 into R1 square plus R1 R2 plus R2 square, or it can be written in this form as well. Now let's move to the second interesting thing. The second interesting thing is about the curved surface area or the lateral surface area of the frustum. So it is very evident now that the curved surface area of the frustum is going to be the curved surface area of the bigger cone minus the curved surface area of the smaller cone. So curved surface area of frustum is going to be, as we know, the curved surface area or the lateral surface area formula is pi RL. So in this case it is going to be pi R1 L1 minus pi R2 L2, because the curved surface area of the bigger cone is pi R1 L1, for the smaller cone it's pi R2 L2. Now I would encourage you guys, take this thing further, because it will have a similar technique as we did for the volume. Just in this case, in place here we had substituted H1 and H2 in terms of H, R1 and R2. Here in place of L1 and L2 you have to bring in L, R1 and R2, and then substitute L1 and L2 in those cases and find out the curved surface area of the frustum, as I have already given you the formula, and the formula is nothing but pi times L into R1 plus R2. I am pretty sure if you try and do it through a similar algorithm, you will get the derivation, get the result on your own. Just in case if you are not able to, your module 4 has this particular chapter where the proof is given to you. You can refer to that, but I would, as I said, I would encourage you to try this derivation on your own. There is a lot of hidden learning into this. So this is about the frustum. Very important things, even though if you are not very much concerned about the derivation, these are the two important things that you should know. Rather, there is a third thing as well. These two things are the volume of a frustum, which is nothing but pi h by 3 into R1 square plus R1 R2 plus R2 square, and the surface area or the curved surface area of a frustum, lateral surface area, is pi into L into R1 plus R2. And as I said, there's a third, one more important thing. So the slant height of this particular cone is L1 minus L2, but there is one more very important thing, that again L1 and L2 are the two things which won't be given to us in the frustum, because L1 and L2 are not a direct part of the frustum. So in that case, how should we find out the slant height? Let's again go back to the frustum. Let's again go back to the original figure. Now you would see this particular triangle, the triangle at the side. Now this particular triangle again would be a right angle triangle, and the hypotenuse of this triangle is L, the slant height which we want to find out, and the height in this case is nothing but H, which is a part of the frustum, which would be given to us, right? And the bottom side of the right angle triangle is nothing but R1 minus R2. As you can clearly see, it is the larger radius minus the smaller radius. So this will help you to find out L directly. So again, apply Pythagoras theorem here and get the value of L directly. L square, as you can see, is directly equal to H square plus R1 minus R2 the whole square. So L is nothing but H square plus R1 minus R2 the whole square under root of that. So this is another important formula. One is volume, one is curved surface area, the third is slant height. As you can see, it is in terms of H, R1 and R2, which is very important. And obviously the total surface area of the frustum is going to be that curved surface area, another very important last formula. curved surface area, which is pi into L into R1 plus R2, plus the bottom surface area plus the top surface area, which is pi R1 square plus pi R2 square respectively. So the total surface area of the frustum is going to be pi into L into R1 plus R2 plus pi R1 square plus pi R2 square. So this is all about frustum. Now let's see a couple of problems of the concepts that we have learned till now. Let's see how well we can apply them.